from the break. Again, my name is Chris Chapman. I'm from the National Center for Education Statistics. I'm also a member of FCSM itself, who's been organizing these workshops. I have the pleasure of introducing our next two speakers and sort of managing some questions afterwards. Just to let you know, we're going to be out of the room by about 4:30, so probably going to cut the questions off around 4:20. I think our speakers are both going to be working within about a half an hour time frame to make their presentations. Our first speaker today will be Dr. Junaid Siddiq. He has a PhD in biostats from UCLA and a postdoc credential work at the University of Chicago. He's currently at Northwestern in the School of Medicine. And he has chaired two sections of ASA, one on health policy statistics and another on mental health statistics. His methodological expertise is in several fields related to this topic. One is missing data methods. Another is what happens to cases that drop out of, I think, longitudinal studies. Data harmonization and measurement error with applications to study of diet and physical activity. His talk today will focus on sensitivity analysis with integrated data focusing on measurement error. Our second speaker today is, I think, soon to be Dr. Ben Ackerman, right? Hopefully, okay. Wish you luck. I'm sure you're going to do great. He got his undergraduate degree at Johns Hopkins, and he liked it so much that he stayed there to get his PhD, where he's now working in the biostatistics department, if I understand correctly. Comes highly recommended as someone who really understands issues in generalizability. In this case, it's generalizing the results of clinical trials, which are randomized, but are usually not representatively sampled to well-defined target populations. He has a lot of methodological work in causal inference, generalizability, particularly with application to autism spectrum disorders, mental health, and LGBTQ health issues. Last summer, 2018, he was a fellow in the data science for social good program at the University of Chicago. And his talk will focus on sensitivity analysis and generalizability. So with that, I'm going to hand the microphone over. And get off the podium. Thank you.
Thanks, Chris, for the introduction, and thanks, Joe, for inviting me. It's always fun to share ideas with people outside of biostat medical field. So I'm looking for the discussion. My talk today is measurement error correction and sensitivity analysis in longitudinal dietary intervention studies using an external validation study. This is joint work with Mike Daniels, Ray Carroll, Raghu, Liz Stewart, and Larry Friedman, and I want to acknowledge funding from NHLB. Outline of my talk, I'll first begin talking about lifestyle interventions, which are interventions to improve healthy behaviors, often dietary behaviors. And then I'll talk about measurement error and self-reported diet as typically how lifestyle interventions measure dietary intake. I'll present the motivating example, which is the sodium intake in the premier study, the lifestyle intervention. Methods.
Yeah, I think you probably have to speak louder, and I think you're getting it gets picked up here.
Okay.
So try to project down.
Okay. Can you hear me better on the phone? Okay, thank you. Then I'll describe methods for measurement error correction, including sensitivity analyses, results and conclusions. And I don't need to get through all my slides. I'd rather we have questions and discussion, so feel free to interrupt at any time. If you don't want to walk up to the mic, I'm happy to answer questions. So lifestyle interventions are longitudinal clinical trials designed to improve diet and physical activity behaviors. And a number of these trials have shown that healthy changes in diet can reduce morbidity and premature mortality, and that effective weight loss interventions can reduce the risk And these are very intensive interventions. They involve coaching the participant to change their behaviors, education and healthy behaviors, self-monitoring of their diet and physical activity, things like this. And often they have to follow some prescribed diet or physical activity. And these interventions typically use self-reported measures of diet. And obtaining accurate measurement of diet and change over time is a major challenge due to measurement. So if you want to assess whether these interventions are working, you need to be able to estimate their dietary intake change, and that can be difficult in the present. So in lifestyle interventions, self-reported diet is often obtained using an interview-assisted 24-hour recall. Considered kind of the gold standard for self-reported intake. And it's a very structured, systematic interview in which a dietitian or nutritionist contacts the person either by phone or in person, and in a very systematic, structured way, asks them what they've eaten over the past 24 hours. And despite the fact that it's just what they ate yesterday, and it's a trained interviewer, there is still measurement error in this estimate because of memory limitations. People don't always remember what they eat. Poor quantification of portion sizes. People don't always have a good grasp of how much they eat. They often tend to underreport their diet. And then social desirability. If you're in person with a nutritionist, you might be hesitant to report all the trashy food. So the measurement error is a huge field, and there's a lot of work, and then a lot of work on it, and a lot of it has been motivated by self-reported diet because common situation. But most of the research is focused on when the dietary intake or the variable measured with error is a covariate in a model looking at some outcome, usually some health outcome. And in that setting, the variable measured with error can distort or attenuate the relationship between exposure and outcome. And there's less research on when measurement error is an outcome. When an outcome is measured with error, especially longitudinal outcome. So the presence of treatment conditions and the longitudinal nature of lifestyle interventions can introduce what I call differential measurement error. So here are some examples of what I mean by differential measurement error. So the study may consist of training and self-monitoring of portion sizes. Sometimes they'll have like little plastic pieces of meat, plastic broccoli to help train people on what is actually one serving. And so you can imagine people might become more accurate over time in the report. Or they might just become more accurate because they're in an intervention study and now they're more aware of what they're eating, they're thinking about it, and they're going to become more accurate. On the other hand, they might become less accurate. These 24-hour recalls, if the participant reports a food that's not in the food database, they'll be asked to list the recipe. You can imagine maybe the second time you're asked to do this, it might be easier just to report a food that doesn't require you to list it. And then in an intervention study, participants may misreport their diet to be more compliant with the intervention compliance. And again, you can imagine you're in a study, you're asked to do something, you might be hesitant. The question was whether we've seen measurement error to differ by other covariates, demographic areas. So it's well understood that BMI is related to measurement. So, the greater BMI, the greater the underreport. That's a well-known one. and we'll control for BMI and all the analysis. Then I'm kind of extending it to talk about differential with respect to treatment condition and with well, gender we also control for as well. There's less evidence about measurement error. The measurement error correction in any context requires some source of additional information regarding the variable measured with error and its true value. And so this information can come from internal validation study. That would be kind of the ideal case where you take a subsample of participants and give them the gold standard along with the instrument that's subject to measurement error. And that's ideal because now your validation study is representative of your external validation study is what we're going to use here, and this is a separate study in which participants receive the gold standard and the instrument. And then calibration equations are obtained from an external validation studies and are basically regression coefficients addressing the gold standard. With self-reported diet, validation studies are conducted using urinary biomarkers. Urinary biomarker is a biochemical indicator of dietary intake, and it's obtained through a 24-hour urine sample. So participants have to collect their urine for 24 hours, and then for only a few nutrients, sodium, potassium, nitrogen, and total intake, can you obtain unbiased estimates. So they're less sensitive to bias we've seen in self-reported assessments because it's objective, but they have this high participant. So we talked about these interventions. There's coaching, trying to change their behaviors, there's self-monitoring, and then on top of all that, asking them to collect their urine for 20 hours. Probably unrealistic. So they're not common in intervention studies. And in the note, which I won't discuss further, is urinary biomarkers are also subject to measurement error, but okay, so the motivating example was the PREMIER study, which was a lifestyle intervention designed to determine the multi-component lifestyle interventions on blood pressure. And there were 810 participants randomized to 3 treatment conditions: advice-only standard of care, established condition where they were given instruction and over 6 months to modify their diet, including sodium intake, and then the established plus dash, which in addition to established components, were also taught to follow the DASH diet, which is rich in fruit. I'm going to combine 2 and 3 together into a single treatment condition. And the goal was in the treatment conditions was to reduce their sodium intake to less than 2,300 milligrams. Yeah, I saw that. Okay. Right. Thanks. So in PREMIER, diet was measured using 2 unannounced 24-hour recalls on one weekday and one weekend. And you can imagine why it's important for them to be unannounced. If you know it's coming, you're going to modify your behavior. And then this was performed at 3 time points: baseline, 6, and 18 months by telephone. Here we're going to focus on sodium intake and specifically the difference in sodium intake between groups. And then following convention, all analyses are based on log transform values. So I said that measurement error correction requires some source of information on the variable measured with error and its truth. And we're going to obtain that information from the OPEN study, which was the Observing Protein and Energy Nutrition Study, a study performed by NCI. And it was specifically a validation study designed to assess dietary measurement error in self-reported instruments. So participants received a 124-hour recall and then 2 24-hour urine specimens over a 2 weeks. So we have we have both the self-report instrument and the so-called gold standard. Not all consumed sodium appears in urine, so we apply this correction factor, and again, we're going to use log transform value. So this is a scatter plot of the open data. On the y-axis, we have urinary sodium, and on the x-axis, we have self-reported sodium. The solid line is a 45-degree line. If self-reported sodium were unbiased, we'd expect the points to fall along that line, but instead, we have the dotted line, which is the regression line, and you see that that's not the case. So people with low self-reported sodium values tend to underreport their sodium. So we see the points above the 45-degree line. Those with higher self-reported sodium intake tend to underreport their sodium. Tend to overreport their sodium, and you see their points below the 45-degree line. So we're going to use this. So we're going to use this relationship in open and apply it to Premier to correct for self-reported sodium. So here are some baseline characteristics of the two studies. They're similar ages. Premier was the inclusion criteria required them to be pre-hypertensive. So you see that BMI is a bit higher in the Premier study. Lifestyle interventions always struggle to enroll men, and so you see a lower percentage of men in Premier than open. And self-reported sodium, mean self-reported sodium is a little bit lower in Premier.
For both of these studies, is BMI measured or reported?
I'm almost positive it was measured in both studies. Sorry, the question was whether BMI was measured or reported in both studies. I'm pretty sure it was measured in both studies. They were coming in from various reasons. So this is Joe told me that in graduate school they call this a Don box after Don Rubin because it shows in gray it shows the observed data, and in white it shows the missing data. So the Y's are self-reported sodium, and the Z's are true sodium intake. Or I'm going to use urinary sodium and true sodium intake interchangeably, although they're different. They're actually different in practice. X are background covariates like sex and BMI that are measured in both studies. D is treatment condition, and we're going to assume that everyone in open belongs to the control condition because open is cross-sectional. We only have open at one time point at baseline, but we have both self-reported sodium and urinary sodium. So the idea we're going to do here is we're going to use this relationship between self-reported sodium and urinary sodium in open, and we're going to apply it to Premier, and we're going to use imputation to actually impute true sodium intake in Premier. Now we got to make a number of assumptions to do this. So the first assumption is sometimes referred to as the transportability assumption, that we need to assume that this relationship of Z given Y in open also applies in Premier. Then we need to assume that this relationship in Premier baseline also applies at follow-up. And I talked about some reasons why that might not apply in a lifestyle intervention. And further, this relationship might be different in the treatment and control conditions for things like compliance bias and things like that. So that's the how of John's talk is how are we going to assess sensitivity? We're going to assess sensitivity to these assumptions about the measurement error relationship changing over time and by treatment conditions. Now, the so-called naive analysis would be to perform our analyses on the Y's, on the self-reported sodium, and our goal is to perform it on the Z's, on and our estimand, or the what, is the difference in urinary sodium at follow-up between treatment. Okay, so I'll quickly define differential measurement error so we can understand the sensitivity now. So Z, I'm going to go through these quickly because I have 10 minutes. Z is the true quantity that we wish to measure time J, and Y sub J is Zj measured with error. X are background covariates, and D is the indicator of treatment conditions. So the first definition is non-differential with respect to treatment, and that's that this regression relationship Z given Y at a given time point is the same in the treatment and control groups. Second definition is non-differential with respect to time, and that's within a treatment condition, this relationship is the same across all time points. Then the third puts them together, that the non-differential with respect to treatment and time, that the regression relationship holds across all treatment conditions and all time. And this idea of transportability is that in two studies, this relationship holds in both, same in both studies. Okay, so the general idea here is to fit a model to the observed data. We don't have a lot of it. We have self-reported in Premier, and then the cross-sectional data in Open. And then we're going to make plausible but unverifiable assumptions in order to identify the parameters from those distributions involving true intake based on incomplete information. We have to make these kind of assumptions about non-differential measurement error. Then we'll generate imputations of true sodium intake in Premier, make inferences, and then we'll go back and do sensitivity analyses to these assumptions we made up here. See how sensitive our treatment effects are to different assumptions regarding differential measurement. So we begin by modeling the joint distribution of true intake and self-reported intake, and we can factor it in this way. But note, most of the parameters of these distributions are not identified because they involve unobserved values. And in fact, only self-reported intake is parameters of self-reported intake are identified in the Premier study. So to kind of help reduce the number of parameters, we're going to make a few assumptions. First, we're going to assume that this distribution of V1 given V0 does not depend on self-reported intake at baseline. And we're going to assume that urinary sodium at baseline doesn't depend on follow-up self-report. I'm not going to do sensitivity analyses to these assumptions. And then the factorization reduces to the I'm going to skip ahead, I think, so we can get to the sensitivity. Okay, and so now to identify this distribution of true intake at follow-up, we have problems here because Z1, Y1, and Z0 are never jointly observed. All from the picture, these Y1, Z0 are never jointly observed. We need to posit associations among these variables. So we're going to do this, and the key one to focus on here, I think, is this non-differential measurement error with respect to time. So we're going to begin by assuming that this relationship at follow-up is the same at baseline, and then we're going to do sensitivity analyses based on this relationship. Under the transportability assumption, the distribution of Z0 given Y0 has the following regression relationship. Except this is the slope on self-report, and then this is the slopes on the background covariate. So under non-differential measurement error with respect to treatment and time, we're making this following assumption that these regression relationships at follow-up are the same at baseline. The regression coefficients are same, and the residual coefficients, the residual variances are the same. So we're going to do sensitivity analyses based on this central. See how, as we depart away from these assumptions, how do our inferences change? So we begin by introducing a sensitivity parameter, and today I'm just going to focus on sensitivity to just the intercept term in that regression relationship. So this is the intercept term from the regression line at baseline, and then we're going to say that the intercept at follow-up is equal to the regression relationship, the intercept at baseline, plus some sensitivity parameter delta. And we allow delta to vary by d, the treatment condition. So when delta d is the same in the treatment and control groups, then you have non-differential measurement error with respect to treatment. When delta d is equal to 0, you have non-differential measurement error with respect to time. So scale delta d by a percentage of the residual standard deviation. So here's the regression line, and as we allow this intercept to change at follow-up, we're assuming either more or less underreporting at follow-up as and we let that differ by treatment. So I'm not going to talk about parameter estimation, except that we use Joe's software to do it, and then we generate imputed values based on the parameter estimate. Okay, and then this is our estimand. It's the difference in change in sodium intake in the treatment group versus the control group. Is less than 0. Reduction in sodium intake is greater in the treatment group than the control group. So here are the results, which I've plotted using a contour plot. The solid dot here is when the delta in the treatment group and delta in the control group are both equal to 0, and that's non-differential measurement error with respect to treatment and time. And here the effect size is small, -0.11, but quite a bit smaller than the effect size based on self-report, which was large, almost -0.5. And then we see that as we vary these sensitivity parameters, our treatment effect changes. So this quadrant up here is the kind of the extreme situation where you assume that at follow-up, participants in the treatment group underreported less at follow-up than they did at baseline, and those in the control group underreported more at follow-up than baseline. You see this huge effect size of -0.1. Here is the opposite, where those in the treatment group underreported more, and those in the control group underreported less. And in fact, the sign of the treatment effect flips. And in between are more kind of reasonable assumptions about how these. In terms of p-values, the non-differential measurement with respect to treatment and time is significant, but very, very modest assumptions about non-differential measurement error, and the treatment effect goes away. And I think this is driven mainly because the effect size is so small to begin with. But if we assume that those in the treatment group underreport more, just a little bit more at follow-up as compared to baseline, and the control group stays the same, the effect is no longer. Questions about this? Sorry, Tom. So we described a framework for measurement error correction. In Premier, corrected treatment effects were small and sensitive to mild assumptions regarding the nature of measurement error. And then if the goal is to produce a single analysis rather than a range of inferences across these different sensitivity parameters, you could draw the sensitivity parameters from a prior distribution to incorporate any kind of uncertainty in what's the correct sensitivity parameter. And in the paper, we did that, and that shows that even when you kind of get the sensitivity parameter wrong, you can still get good coverage for your. And then this is the paper this talk is based on in biometrics. It's still in press.
All right. Thank you, everyone. Invitation and for here, I'll microphone a little bit. Okay, I see the Polycom. Great. So thank you again for the invitation to be here and to speak and be a part of this session. Today I'm going to be focusing on statistical methods for generalizing findings from clinical trials to well-defined target populations, and motivate some sensitivity analyses around when some of the key assumptions to implement those methods don't hold. I also want to acknowledge Trang Nguyen and my advisor Elizabeth Stewart at Johns Hopkins, who have been instrumental in driving this work forward. So I'm first going to give a hopefully brief background on the methods for generalizability and why this problem exists. And to start, I want to motivate this talk with some relevant research questions. So the focus here is research questions that have implications for populations. So for instance, Medicare may be deciding whether or not they want to approve some payment for a new treatment for back pain. Another possible research question is, we may have a public health media campaign over switching car seats to forward-facing at a certain age. We want to evaluate the effects and predict the effects of that campaign in the overall population. A healthcare system or a hospital may wish to predict the effects of some new evidence-based intervention in their patient population, and then a physician practice may want to decide whether or not training providers in some new intervention would be cost-effective among their providers. And so the gold standard for answering some of these research questions using rigorous causal inference is to use a randomized trial. So to implement an RCT, we know that these are the gold standard for estimating causal effects, given their strong internal validity. So because we randomize the treatment assignment, we're allowing for unbiased estimation of the sample average treatment effect, which I'm going to refer to in this talk as the SATE. However, given a lot of the research questions on the previous slide and others as well, we may not actually be, we may be interested in the SATE, but more broadly, we might be interested in the target population average treatment effect, or the TATE, as I'll refer to in this talk. A commonly known issue with randomized trials, then, is that they often have poor external validity, or generalizability. And this comes down to several factors, one of which is a lot of trials have strict exclusion criteria, and so therefore the samples we have in randomized trials don't really represent the target population of interest, and there may be lack of attention paid to that target population when the initial trial is recruited for and implemented, and so therefore our estimate of the SATE may not equal the estimate of the TATE. And this Cole and Stewart paper is a really nice one in formalizing where this bias comes from. And it mostly comes down to if there are treatment effect modifiers, so factors that impact the treatment effect that differ between the trial and the population. So if people of an older age respond better to some treatment and your trial is generally older than the target population you care about, this is where we might believe that our estimate in the sample may not generalize well to the population that we care about in that case. And I just wanted to also give a note that this is sort of similar to issues arising in the survey world around non-probability sampling. And so there are several things we can do to address generalizability at different stages. The first of which is through study design. So where we can ideally select subjects for a trial in a particular way, whether it be generate a random sampling from our population, which I've noted is great but rare. Particularly in the education research world, there's been a lot more work in better study design of trials such that they're representative of the target populations we wish to study. Beth Tipton at Northwestern has a lot of great work in this area. But for the medical field, in medical RCTs, it's much harder to implement some of these changes at the study design phase due to cost, the resources that are restricted. So we can do certain things with study design, but often we're left with what can we do once the participants are already recruited and the trial is run. And so the remainder of the talk will be focused on some post-hoc statistical methods that once the trial is already completed, what are some ways in which we can evaluate the generalizability of a trial and ways to improve upon the generalizability using statistics. I listed 3 different approaches, the first of which is a weighting approach where we fit a model of trial participation. We can weight the trial to better resemble the target population on our observed pretreatment covariates. And I also noted this is similar to the propensity score world of ATT weighting for non-experimental studies. There are other approaches where we can model the outcome using machine learning, using our observed covariates, and then predict the outcomes in the target population. And then there's been some recent work on doubly robust methods where we're both fitting a model for the outcome and also a model for the trial participation probability. And so I think this area of research fits nicely in this session with FCSM and integrating data because implementing these methods requires having some data both for the trial itself, but also having a data set that describes the target population of interest. So for the methods described here and that I'll talk about, we can't just use summary statistics of our target population on age, sex, and race, but we actually need a data source on that population. So I have a figure here that shows for the trial, we observe the outcome, we observe treatment, and a set of covariates. And then we ideally would like to find a population data set, which commonly now come from federally, nationally representative surveys. So I've probably used a lot of data sources from many of your agencies. Thank you. But we don't observe the outcome or the treatment assignment in that data source, but we do ideally have the same set of covariates that are treatment effect modifiers that are relevant to the issue at hand. And I also want to note that there is also some software in the works to implement these methods using R. So I know R is slowly invading government agencies. I'm a big fan. So now to motivate the sensitivity analyses, in order to implement these methods, we need to make some assumptions. And I've listed sort of the 4 standard assumptions here for implementing the weighting and the outcome model-based approaches, where we first need to assume that all members of the target population have a non-zero probability of being selected in the trial. We then need to assume that the range of the effect modifiers in the target population are covered by the ranges of the respective covariates in the trial. So the situation of overlap, saying that if we have a trial of people aged 20 to 40, we can't generalize to 60-year-olds and above. We also need to assume that treatment assignment is independent of sample selection, as well as the potential outcomes given the pretreatment covariates. And then lastly, and this is where the sensitivity analyses are motivated by, is this assumption that no unmeasured variables are present that are associated with sample selection and treatment effects. And so in practice, this is often a very difficult assumption to make. Yes, you have a question.
How, the first assumption, earlier you said how very often the trials
So the question was, how valid, given strict exclusion criteria, is this first assumption of all members of the target population having a non-zero probability of trial selection? That's a good question, and I think one point I'll also make is that defining the target population is tricky, but also really important. And so you do need to think carefully about how you're defining the population and also who is in the trial, because we can't do magic and extrapolate past people who have no chance of being in the trial. So that's a good point. So this last assumption of no unmeasured treatment effect modifiers is one that's often, we have to make it, but may not always be a reasonable assumption to make. And so, for example, what if there is a treatment effect modifier that we observe in the trial, and this variable is collected because researchers conducting the trial believe it's something influential, but we don't have data on that variable in the data we have for the target population of interest. And then further, what if we have concern that there is some treatment effect modifier that's not even observed in the trial? So say we have some fully unobserved treatment effect modifier. So as I mentioned, this issue of unobserved treatment effect modifiers is actually very likely given the real-world data that we have. So particularly when looking at the target population data we have available, there are often very few covariates that are observed consistently between the trial and the population data. And then further with population data, there may just be a restricted set of measured factors that do not include all of the variables that are measured in the trial. So today I'm going to be focusing on some parametric sensitivity analysis strategies for how to handle when we have both partially unobserved and then fully unobserved treatment effect modifiers. I also want to note that there are some other approaches using bounding as well. So I'm going to present two different cases of sensitivity analyses. This first case is going to be when we have a treatment effect modifier that's observed in our trial, but is unobserved in the target population. I'm going to call this the V case. That will make sense when I go into the notation in a minute, but just remember, partially unobserved is the V case. And then the second case is when we have a potential treatment effect modifier that's unobserved in both our trial and our population. And this will be called the U case. And I also wanted to note that these are somewhat analogous to some sensitivity analyses for unobserved confounding in the non-experimental settings. And these are great papers to check out if you would like to read more on them. So I'll give some brief notation for the sensitivity analyses. I'm going to use A to denote the treatment assignment, which is randomized in the trial and not observed in the target population. The outcome will be denoted by Y, which is, again, only observed in the trial. Y of A will be the potential outcome, Y under treatment A. And then I'm going to use S to denote sample membership, where S will equal 1 if person I is in the trial. S will equal 0 if the person is in the target population. And I also want to note a subtlety in the setup here, given that I'm assuming the target population and the trial are disjoint sets of data. This is technically what some would refer to as transportability, but the same ideas apply here. And then I'm going to define the state to be the average difference of potential outcomes in the trial. The state will be the same, but in the target population. So X is going to denote all non-effect modifying covariates. Z will be an effect modifier that's fully observed in both our trial and our target population data. And then going back to those two cases, V will denote a treatment effect modifier that we do observe in the trial, but it's not observed in our target population. And then U will be this capturing of all fully possible unobserved effect modifiers that we don't observe in either. I'm going to describe the V case for the partially unobserved. We're going to assume a model for the outcome that holds in both the trial and the population, where our outcome Y is going to depend on treatment. It's going to depend on Z, the fully observed treatment effect modifier, and V, and then some function that we care a little less about of X, Z, and V. And so therefore, the tape is going to be defined as the following, where we have an effect from treatment, that's beta A. We have the effect of Z on Y through beta ZA, and the mean of Z in the target population. And then we have beta VA times the mean of our covariate V in the target population. However, since we do not observe V in the target population, I'm going to highlight it in red as something that we cannot estimate. And so that's where the sensitivity analyses come in handy here. And there are two approaches to sensitivity analyses here. One is an outcome model-based sensitivity analysis, where we're going to first estimate the beta parameters using the trial data, where again, remember that V is something that's observed in the trial, so that's where we can estimate it from. And then we're going to obtain the mean of Z in the population, because Z is something fully observed. And then we're going to specify a plausible range for the mean of V in the population. And this can come from using knowledge of V in the trial. It can be specified through other outside sources of knowledge, but this is where the sensitivity analysis will come into play. And then we'll combine all of those to obtain a plausible range of the population average treatment effect and some measures of uncertainty. And then there's a weighted outcome model-based approach where we do all of these steps, but first we're going to weight the trial sample such that it better resembles our target population with respect to the factors that we observe, X and Z. And we again estimate the parameters in the trial, specify our sensitivity parameter, and visualize them. So I'm going to give an example of this V case using data. So here we have a smoking cessation intervention for heavy smokers among attendants of alcohol and substance use treatment. And the trial found a treatment effect of 10 fewer cigarettes per day, I think is what it says, but that gets cut off by the call. Our Z variable of interest, so our treatment effect modifiers that are observed in both our trial and our population data, and I believe here that the data we're using for the target population come from NISDA. And that represents people who are seeking alcohol and substance use treatment who smoke heavily, is how we're defining our target population. So our treatment effect modifiers that are fully observed are race, so being African American, and baseline daily number of cigarettes. Another factor that was measured in the trial but not available in NISDA was a baseline addiction score, which was shown to moderate treatment effect in the trial, and that had a mean score of 4.05. And so in the figure below, what we have is on the x-axis, we have a sensitivity parameter where we're going to vary the mean baseline addiction score in the population that we don't observe that variable. And we're going to see how on the y-axis our estimate of the population average treatment effect varies. And in red, we have the outcome model-based approach that I described. And in blue and in the dotted line, we have the weighted approach, where we pre-weight the data by X and Z in the trial, and then conduct a sensitivity analysis. And so we can see how sensitive the results are as we vary the different possible values of the mean baseline addiction score in the target population. And so we can get a sense of when we have a violation of this assumption of no unmeasured treatment effect modifiers, we can get a better sense of a plausible range of the treatment effect in the population. And I'll note that the weighting approach obviously has a wider confidence band than the unweighted. So now I'm going to describe the sensitivity analyses for the fully unobserved case. And so here we're going to think about U as being the remaining composite effect modifier. So what if there are factors that were not measured in the trial even that could moderate treatment? So this captures all unobserved factors, and we're going to assume it's independent of the observed covariates and the effect modifiers. So unlike the previous case, we can't use that nice formula we derived because we don't have U observed in either data sources. So what we're going to do instead is use a bias formula, and this bias formula is one that builds off of the findings in that Cole and Stewart paper on generalizability. And we're going to define delta U as the difference in U's mean between the trial and the population. And then through some derivations that, given time, I'll just skip over, we see that we now have two sensitivity parameters. We have that delta U, so this is the third line up from the bottom. We have delta U, which is the difference in U between the trial and the population, and then the effect of U on the outcome beta UA. And so the last line is just describing for the weighted approach when we weight out X and Z. And so similarly to the V case, we have two approaches. The first is this bias formula-based sensitivity analysis where we're going to estimate the things in black using the trial and then specify ranges for that effect size and also the difference in U between the trial and the population. And then the weighting approach where we're first going to weight the trial, again, to resemble the target population with respect to X and Z. Similarly, we can obtain a plot of the target population average treatment effect as these two factors vary using this cool 3D graphic. And so here's an example where we've altered the data a little bit to reflect the methods where we're using a trial that compares a new antiretroviral therapy regimen to an old one, and that trial found an increase in CD4 count by 36 cells per milliliter at 2 months post-treatment. And so our Z of interest, the treatment effect modifier, is being white and not having severe immune suppression, and we're also using age. And then we're concerned about if there are any unobserved factors U for which we specify a range of 0 to 0.7 of the effect of U on Y, and we are going to specify a range, a difference between U in the population and the trial of 0 to 0.7, and we're going to vary the effect from -15 to 15. So this figure, I don't know, might be a little small from here to see, but we see on the, I don't even know which axes these are. So we have the difference between U and the trial and the population. This one. The other horizontal one is the varying of the delta U, and then on the vertical axis we have how the population average treatment effect varies. And the yellow on top and bottom are the confidence bands of that varies. I also just wanted to quickly note an extension that we've been working on for the Z case. So suppose that we have an outcome that's not continuous, but is binary, and we're concerned of a partially unobserved treatment effect modifier. We are going to define P of A to be the probability of our outcome occurring under treatment A, and define our target population average treatment effect as the average odds ratio in the target population. Similarly to the V case, we're going to assume an outcome model where the logit of the probability of the outcome depends on that similar form of the treatment and the treatment effect modifiers, and therefore we can derive that formula formula on the bottom for the target population average treatment effect. But since, again, V is unmeasured in the population, we cannot estimate that, and so using some moment generating functions and making some additional assumptions on the distribution of V in the population, we can identify two sensitivity parameters here, one for the mean of V in the population, one for the variance, and we can perform the same types of sensitivity analyses. This is just to note an extension, and we're also working on extending to other types of outcomes. So to wrap up, when we're concerned about generalizability of trials, we do have some great tools to improve upon the generalizability of them and to make population-level inferences. And when we are concerned about certain violations of unmeasured treatment effect modifiers, we can conduct sensitivity analyses to show how sensitive our findings are to unmeasured factors. Another limiting factor we have are population data availability, and so we do recommend that if you can find population data that have as large a set of measured covariates as possible, that would be best for satisfying this assumption, but when that's not possible, sensitivity analyses like these can be helpful in testing those assumptions and providing a more robust conclusion of results. With that, I have small references, and thank you very much.
I have a question for the young man. So your data, you have the V case and the U case, and you showed us, can I do a previous on this? Is that all right? If it's not letting me go previously. At one point you showed us, for the first case, for the V case, showed us a confidence band? Yes. Okay. So I was just wondering whether you looked at, I assume that you're interested in the weighted data because you feel like that is more representative of the total population. And I'm wondering whether the larger band is being driven by any particularly large weights, and if you consider weight trimming, if it has that.
That's a great question. I also want to note that I was not actually involved in this particular data example, so that's a good question. I know there are also some simulations done with this paper to evaluate the different approaches of weighting and not weighting, but in terms of this, I'm not sure if there were any large weights in particular.
So I have a question directed mainly at Ben, but Sinead, if you can answer it too. So these sensitivity analyses that often arise in the area, say, of causal inference with non-randomized treatments, or in this case, you have these this generalizability problem. You're often trying to say there is some unmeasured variable out there which is causing problems, and we want to say something about that unmeasured variable that's coming things up. It's hard to imagine the entire universe of unmeasured confounders and unmeasured treatment modifiers that might be out there. And I always found that really difficult to grasp, how to do a really rigorous, more rigorous kind of sensitivity analysis with these nebulous things that are not really, where you have variables out there that people haven't even necessarily imagined yet. Is there anything you can say about how to make that a little bit more rigorous?
certainly think that it's tricky to think of, what are the things we don't know that could be at play. So you're asking how to make sensitivity analyses more rigorous, or thinking about them?
Yeah, thinking about this, because I think a lot of this, and I don't know this literature well, but a lot of it goes back to that study by form the basis. I'm just wondering if you have run across any examples where analysis did a particularly good job of making that compelling, rather than, it really, anything comes to mind about where to look.
Like my advisor, but Stuart would be great at coming up with some examples.
This is a paper by David Haziza, who made who estimated how this unobserved covariate would affect variant and bias. And it was a relatively recent paper that I forgot the exact reference. But he did analytical derivation.
David is very prolific.
If I find it, I will.
Thank you.
Another thing I'll just note is, I know sometimes it can be tough to translate the papers on sensitivity analyses into practice. And so one thing that we tried doing was also writing up more of a tutorial sense of a paper for actually implementing these ideas in practice. So I think it's like the paper is in +1, where we sort of provide some guidance on how to think through when there might be unobserved treatment effects modifiers and how to actually implement some of these.
About your software?
It's still in its most basic version, but it's so it's an R package that was on GitHub, and it has two functions. One where a user can assess how generalizable their trial results are to a population, and one where they can then implement some of these post-hoc statistical methods, so using weighting or some of the flexible outcome model approaches. So again, the idea is that it requires having some stacked data. You have your trial, and then you have the target population. Specify what are the variables that denote treatment, assignment, sample membership, and the covariates. And then you can see some nice summaries with relatively little amounts of code. But also note the sensitivity analyses are not incorporated in the package yet, but it's one we're working on.
By the way, for a great presentation. Actually, this question is more for Janae. You had laid out model parameters that you were going to go ahead and do direct testing of. But you had set aside a couple of theoretical questions that you could maybe have taken a look at, but you just took as given. And I think one of them was, like if there was change over time in either the control group or the treatment group, you weren't going to necessarily deal with that directly. I might be misremembering. But things that you didn't actually try to delve into, did you have conceptual reasons for not doing that, or you just wanted to focus on something you could actually solve? You theoretically could also deal with these other parameters, but you didn't spend resources on them just yet.
That's a good question. I went through that kind of quickly. There were lots of unidentified parameters, not lots, but there were some other ones, regarding associations between self-reported urinary sodium And I think overwhelming. You kind of have to focus on those that you think are most critical. You know, the kind of the assumptions are at least valid, and also are most likely to drive your inferences. That's how I focused on the differential measurement error. But you're right. I mean, I could have, just looking at two at a time, you saw that contour plot, and there's a huge range of inferences. Start looking at more than two at a time.
As a follow-up to that, so I noticed that both of your presentations, you had two sensitivity parameters, and so it was and that's a step up because papers that were being published not long ago just had one. So two is good, but as Chris mentioned, in reality there tends to be a lot. And what would you think about what might be a way to start to approach the problem of assessing the sensitivity to lots and lots of parameters that you really can't estimate? Do you have any thoughts on that?
One idea that I talk about in the paper is I use kind of point mass priors for these different sensitivity parameters. But you might imagine that they're correlated. For example, whether the treatment group and the control group, they might both tend to over-report or both tend to under-report more. They kind of might be correlated and move together. And so that can kind of maybe constrain the inferences a little bit, so you don't have. That also allows you to kind of incorporate uncertainty. That's one thing.
My view, I don't know, it's almost impossible to make this kind of analysis. Only way to make it is to include output variable in your model. And it's also very difficult. I know Jules Shaw works on that, but his results are difficult to interpret. But that's the only way.
I'd like to thank both of the speakers in this session. They were a really nice compliment to our earlier presentation by Sharon Lauren. We really appreciate the biostatistics world and the insights that they can offer for those of us who are in other parts of the overall statistical community. One point that the statistical community, federal statistical agencies, and others wrestled with is a question of, well, you do these sensitivity analyses, and then what do you do with them at the end? One point that was where we saw a kind of a flurry of advocacy perhaps 20 to 30 years ago was to say, well, if you do these sensitivity analyses and they indicate that what we don't know could really hurt us a lot, the statement was, therefore, we really ought to be collecting data to, in fact, fill in those gaps. A couple of places where this came up was Bob Groves and others advocating for, quote, designing for non-response. The idea was incorporate in your data collection process certain variables that are not necessarily of substantive interest of themselves. You're not going to publish a mean estimate, for example, for whatever the variable is, but it may be crucial, for example, in modeling the non-response behavior and thus proving some kind of adjustment, or perhaps informing field interventions. In addition, at more or less the same time, there was some advocacy for, quote, designing for small domain estimation, unquote. The idea being that as opposed to simply saying, we're going to have a particular exercise, give me the mean for a progressively smaller group, we recognize, gee, we need to do some modeling, In some cases, that modeling may benefit from having certain kinds of regressors that, again, are not necessarily of substantive interest themselves, but may be really crucial in terms of improving our model fit to the point where we can do a better job of effectively predicting the Ys for which we do want to get some kind of estimate. And the obvious implication is that in many cases, both for the biostat cases that we've seen in the second session and arguably some of the, I call it social and economic cases we were seeing in the first session, is you could ask, does this offer insight, does a certain set of sensitive analyses offer insight into that further, quote, design for, and then fill in the blank, whatever the limitation is that we have. I wanted to ask our biostat colleagues whether you have seen that show up in the combination of the clinical trial world and the population-based study world in which you are attempting to bridge those gaps, and has it led to cases where you will, for example, expand a clinical study so that you're capturing certain variables to help you do that kind of bridging?
I might not be the best person to answer this because I've only had 4 years of graduate school to see things at play, and things take a long time.
We're giving you the assignment for the next 30 years, though.
Great. Yeah, I mean, I've definitely seen like a push for more data collection in terms of what might be available in like larger scale surveys that are being used to represent populations. I think there's also a really great opportunity in, and I mean, people throw the term big data around a lot, but in the availability of things like electronic health records and claims data that have sort of unprecedented amounts of information. So I think there are a lot of great opportunities to utilize some of those data sources as well that maybe are collecting a broader set of variables, even if they might not appear in the same traditional way that we're used to. But they might be embedded in something else, or like insurance claims.
I've seen things in like a cohort study in my department where we measure people every 5 years or so. If they missed the previous study time, we'll ask them, why did you miss last assessment, and that can be used when modeling that response. In my context, the obvious one would be to do an internal validation study where you get, urinary measurements on at least a subsample, and to do it not just at baseline, but that's expensive.
Yeah, I'm just curious about the first talk on the actual methods. Is that you said that you did urine sampling and you were able to measure 4 different quantities, and at the same time you asked people about their diet, what they ate. And I'm just wondering if you use the combination of those pieces of information to estimate the portion sizes.
So we only had urinary sodium in the premier study. But you can obtain total energy expenditure through urinary sodium. So that's something we're kind of interested in, is measurement error correction for when you don't have the urinary biomarker. How much they completely, and some of these others, can you kind of back into that, but we haven't. I didn't. Oh, sorry. The question was, what about exercise? It was an intervention. Can't remember if physical activity. It was probably one of the part of the education. And did people sweat, and did that affect their study? I mentioned that correction factor. You know, but maybe if they're sweating more than usual. But yeah, I did something to think about. Right.
We'll let Joe close out the session, but I did want to, thank Joe and Wendy for organizing the session today.
Yeah, I don't really have anything to say. John, is there any announcements? One announcement is Wendy, don't forget the computer. Okay.
Everybody said their slides are okay to post?
Slides are okay to post? Yeah. John, do you have anything?
Want to thank everybody for participating both here in the room and also on the phone. I have one general suggestion to make. This is June, and as we know, June and July of every year is a good time to think about organizing conference sessions for upcoming conferences in subsequent years. We've had a really good conversation, I think, here today. We really appreciate, especially Joe and co-organizers for making a really very successful attempt to bridge a gap and help enhance a conversation between what you might call traditional social and economic measurement folks and biostat folks. That's something we need to be doing a whole lot more on. It would be very much worthwhile to be thinking over the next month or two about ways in which we can take the ideas that we've explored here. I think all of the speakers in various ways raised more questions than they answered, and that's by design. But it may be worthwhile to think about what may be appropriate selection of material that we might explore further in subsequent events. For example, joint staff meetings for 2020. In some cases, especially if you're looking at social areas, may be appropriate for APOR, Biometric Society meetings, other things like that. So we very much encourage starting here, but also continuing the conversation in lots of different ways. Okay. And I'd like to add my thanks to Joe, Wendy, and Chris for all the work they did in organizing this. So, speakers. I think with that, we'll close. Ben, thanks very much.